last class we actually developed the concept of mean temperature in a fully developed flow, right. So, mean temperature was a useful quantity because it was a radially averaged temperature essentially. So, the temperature was averaged in the radial direction, and we introduced the concept of mean temperature, and we wrote this particular equation. If you look at the presentation, R naught rho Cp into U, where U was the average axial velocity, correct, okay, and Q double prime was the heat transfer or the net heat transfer from wall to the fluid. That was a concept that we developed. We also found that while developing this concept, okay, we found that Tm, which is the mean temperature, is actually given by this. We did last class. So, I am just noting down the key quantities U, Tr, Dr, d theta. This U is basically the local velocity, T is basically the temperature field, right. So, T in general is a function of both x comma r, right, whereas your mean temperature should be a function of x only, because we are taking care of the r variation away, right, because that is what the integral, the purpose of the integral exactly is. Okay. So, also we defined H, which is basically the heat transfer coefficient, is basically T naught minus Tm, okay, where T naught was basically the wall temperature. Okay. So, that was the whole exercise that we did in the last class, where we defined these three important quantities, and from here we thought that the temperature we have to find it in some way. So, our motto is to basically find what is this temperature field x comma r in the fully developed regime. Like for example, in the case of velocity, okay, we found that in the fully developed regime the velocity u, okay, was a function of r only, right, okay, and it was not a function of x. This we found in the fully developed regime, right, in the fully developed regime. What about t? The question remains, what about t, whether t is also a function of x, is a function of r, or is only a function of r, and things like that, right. That is what we need to answer, okay, because based on that we can find out what your Tm is going to be. Once we find Tm, the all important quantity once again is the heat transfer coefficient, which is a function of Tm in this particular case, right. So, all these things are kind of coupled with each other. So, T is needed, okay. So, let us take the formulation based on a round pipe. So, our basic problem is therefore a round pipe, okay. So, the equations will be a little different, okay, from the Cartesian coordinates, is basically theta symmetric, okay, no variation in the theta direction, and it is fully developed, okay, both in terms of temperature and velocity. Of course, we do not know what the fully developed temperature profile is going to look like, that is what we are going to find out. Velocity profile is already known, that is what we did in the last class, right. Now, fully developed means that even the thermal boundary layer, okay, I am not saying that the two boundary layers have the same entrance length, that is not the question over here. So, if this is the round pipe that you have, this is the center line, it is possible that this is your XH, which is the hydrodynamic boundary layer merged, okay. So, from here onwards x greater than XH is what we call hydrodynamically fully developed, right, whereas, okay, the temperature profile may be something like this, okay, or it can be also something like that, okay, whatever, depending on whatever is your Prandtl number is. This, say, call it xt, So, if x is greater than x t, okay, we call it thermally fully developed. Okay. So, if x is greater than x t, we call it thermally fully developed. If x is greater than x h, we call it hydrodynamically fully developed, the two boundary layers over here. Okay. So, we are in a regime in which x is greater than both x h and x t, that means we are somewhere here. Okay. So, that will be like your velocity profile, which you already know, parabolic, and we want to know what is the temperature profile here, right. So, that is the unanswered question that we have. Okay. So, let us write down the governing equation, because we already know the momentum equation, because the velocity is a known variable over here. We just go on to the energy equation at this particular point. So, the energy equation u dt dx plus v dt dr alpha t dr square plus 1 by r dt by dr plus del square t by del x square. That is the full energy equation written in polar coordinate systems, right. And of course, we know u is only a function of fr, and we know v is equal to 0, right. These two things are already pre-known, right. So, what you can write, okay, by simplifying this equation, so it will be alpha dt by dx is equal to delta square r square plus, okay, 1 by r dt by dr plus t dx square, right. Okay. So, that will be the combined equation after we take off this particular term, right, and we write ur as a u as a function of ur only. Okay. Now, there are three main terms in this particular equation, right. So, this is what we call the axial convection, right. There is the axial convection, right. This is what we can call it to be radial diffusion or conduction, okay, and this one is called axial conduction. So, there are the different modes, right. So, you have the axial convection, then you have the radial diffusion, and then you have the axial conduction. The idea of framing this equation now is that we have to find out which terms are important, which terms we can safely leave out. Okay. Obviously, we have to show some legitimate reasons why we are actually deleting some of the terms. So, let us do an exercise in scaling once again, and let us see whether that makes sense in this particular context or not. Okay. So, let us take it term by term once again. Okay. So, what about dt by dx, right. dt by dx is nothing but q double prime divided by rho Cp u into d, right. Okay. And d square t by dx square is basically q double prime rho Cp u into d, that x factor comes into the picture. Let us put this very nicely. Okay. 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 So, the first, so we know dt by dx and we know del square t by dx square, right. These terms will be known right now. Okay. And of course, there will be the last term, which is basically dt d square t by dr square, right. Now, that will be given as delta t, right, divided by d square, because we already know that r has reached d, that means the center of the pipe, right. So, basically this comes because of the fact that thermal diffusion has reached the center line. Got it? Okay. So, let us now take term by term. So, the first term will be u by alpha q double prime rho Cp u d, okay. That is the first term. This should be delta t by d square right. So, that is basically the radial term, the radial diffusion terms, right. Okay. And you have 1 by x q double prime rho Cp u into d, right. That is the axial conduction term, right. Now, pay attention, this how we got this, because we used the corresponding formulation. If you remember that how we found out the dt by dm kind of a term, okay, it comes readily from there. You recall the term, right, that dtm by dx was actually equal to 2 q double prime r naught rho Cp, okay, into u. Okay. This was already pre-given, right. So, using that we are actually utilizing that to find out what are the scales of this particular factor is going to be, right, because the mean temperature gradient is also similar to the axial temperature gradient, right, because we are more concerned about, because dTm by dx is basically has taken care of only the radial part, axial part variation is still there. So, that is exactly what we have used in this particular scaling, okay, utilizing this, okay, which we already did earlier. Okay. So, now that we have all these terms, okay, let us multiply all the terms by, so multiply by d square by delta t, right, all the terms. Okay. So, the first term will become u by this q double prime rho Cp u d into d square by delta t, this is proportional to 1 comma 1 over x q double prime rho Cp u d into d square by delta t, right. That is the terms that we get, okay, right. Okay. And we also know h is given as q double prime divided by delta t, right. Okay. So, let us look at term by term once again, okay, using this definition. This is basically your heat transfer coefficient, okay. Based on this, based on the definition, you have h d by rho Cp into u proportional to 1 over x h d rho Cp u, okay, got it. Okay. Now, if you look at this first term, this u and u gets cancelled with each other, okay, and you have alpha into rho Cp. What is alpha? Alpha is basically k by rho Cp, correct. So, the first term becomes h d by k, that is proportional to 1 or of the order 1, okay. This becomes h d by k into k by rho Cp, okay, into 1 over ux, this is the third term, right. So, this we already know that this is readily the definition of your Nusselt number, right, definition of your Nusselt number. This is h d plus some more terms that are situated over here. So, let us look at the nature of this particular term in general. So, this h d by k is the first term, alpha by u d is the second term, and then d by x is the third term, right. I have just written it in a more compact particular notation, right. Okay. Now, we already know that d by x is a number which is less than 1, right, because x is the length scale. So, x would be normally more than d, right. We are talking about pipes like that, right. So, this term will be less than 1, we know that, right, this particular term only the one which I have circled, okay. Now, what about this term? We do not know anything about the nature of this term, like alpha by u d, right. Okay. The nature of alpha by u d is unknown, okay. But however, if we define a number called Pe, okay, which is called Peclet number, and we say that that is ud by alpha, okay, and if we say that that Peclet number is much greater than 1, right, that means alpha by ud should be much less than 1, right. In other words, this second term within the bracket will be much less than 1. In that particular case, what will happen, this entire term h d by k into alpha by u d into d by x, all of this term will be much less than 1, okay, or rather instead of saying much less than 1, much less than h d by k, which is the term on the left hand side, or in other words we can say that axial conduction conduction is low or negligible. Got it? Okay. So, in other words, we are left with only the term involving the axial convection and the radial diffusion, or in other words, we are left with only Hd by k proportional to 1, right. So, two important things that we have got out of this exercise. Okay. The first one, the most important thing is that Hd by k is of the order 1. Okay. This means that Nusselt number is of the order 1. That means that Nusselt number in the fully developed regime is not a function of x or r, right, not a function, okay, and it is basically a constant, right. That is the first thing that we got. Okay. Let us look at what is the second thing. The second thing that we said, the most important thing that we said is that Peclet number is much greater than 1, or in other words, ud by alpha is much greater than 1. This is a new quantity that we have defined, right. So, what is Peclet number therefore? Okay, Peclet number is basically given by the rate of advection, right, divided by the rate of diffusion, right. Okay. So, this is what is Peclet number. So, that means high Peclet number means that the rate of advection is much more than the rate of diffusion, right. So, in the high Peclet number limit, okay, we can say, right, that okay, the axial conduction is very weak, right, compared to axial convection, right. That is exactly what Peclet number actually says. That means your rate of advection is so high compared to the rate of diffusion, right, that you can actually neglect the axial conduction effect, because it is a very small number in the high Peclet number limit. That means if your flow is very sluggish, say for example, that is barely creeping, okay, and this Peclet number much greater than 1 limit is not applicable, right, then what you cannot apply, you have to carry the axial conduction term with you, right. So, you cannot simplify this equation in this particular way, right. So, this is like an eye opener. We saw two very important things through this scaling argument. One is that axial conduction in most cases are negligible, because we are dealing with a convection problem with reasonably high Peclet number. That is always the case, okay, whatever flow that you are going to deal with, okay, because you have this factor u. Alpha is normally a very small quantity, right. So, if u is substantially large, this number will be probably substantially large than, I mean more than 1. But the most important finding was that based on these two limits, you have that your Nusselt number becomes a constant, okay. So, that means whatever, that means if you have to draw heuristically, that means if you look at this particular plot and this is Nusselt number, this is x being the distance from the inlet of the pipe, right. Okay. Now, intuitively, as you know that so let us say that this is basically the developing region, and this is basically the developed region. So, we are basically looking at the Nusselt number in the fully developed region, right. Now, in the developing region, we all know that the boundary layer thickness is growing, right. It has not touched the middle of the pipe as of now. So, naturally, as you know still that H is proportional to 1 over delta T, that means Nusselt number is also proportional to 1 over delta T, right. So, that means the Nusselt number value is going to be very high in the developing region of the pipe, right. So, if you talk about it like this, the Nusselt number value will probably come out as very high, but as this delta T goes on increasing, the Nusselt number value is coming down, right. So, in the limit it will become something like this, right. So, it is very high here and it is absolutely flat here, okay, and this value that you get is of the order 1, right. So, anywhere between 1 to 10. something like that. It will be your Nusselt number value regardless of whatever you do, right. So, it is very high initially, asymptotes and comes and becomes this flat line, okay, which is not a function of x anymore, okay, in the fully developed regime, right. So, that is a very important conclusion, that this is the region of high Nusselt number, this is the region of constant Nusselt number or a heat transfer coefficient. Okay. So, this particular finding is one of the most important thing which you did not get in a flat plate boundary layer, right. Okay. There the Nusselt number was still a function of Reynolds number raised to the power of half, if you recall, right. So, here of course, the Nusselt number no longer remains a function of your x anymore, okay, which is one of the most crucial findings that you have. Okay. So, now what we are going to do, now that we have established the full fledged equation, right. Now, the next half of the business will be to determine what will be the temperature profile. We still have not done anything to the temperature profile. All we have done is that we have made a couple of very interesting observations. We have reduced the energy equation to a very nominal form by neglecting most of the terms. Okay. So, there are three purpose things that we achieved. We reduced the energy equation, okay. We saw that in that limit Nusselt number becomes equal to 1, and we saw that of course actual the Peclet, this is a limit, this analysis is only valid for high enough Peclet number, right. So, if Peclet number is low, then you cannot apply this particular limit anymore, right. Okay. So, let us look at the first energy equation, okay, and let us look at the what we can do with it. Okay. So, energy equation now in its revised form is u by alpha dt by dr, sorry, writing too close to the, okay, u by alpha dt by dr is equal to okay. So, that is the first thing, and once again this equation now you see is devoid of the axial conduction term, right. So, once again fully developed u comma t, okay, the interest, so x is greater than xh comma xt, that means we are in a region which is far away, and of course we got that Nusselt number is of the order 1. Okay. Now, let us look at how can we define a temperature profile in the fully developed regime, right, which will be a function of r. Like in your velocity profile, we had velocity was a function of r only. Temperature is not that simple because t is a function of x comma r, but can we do some variations on this t so that it becomes a function of both r only with respect to r, right, but normal t is a function of x and r. Okay. So, let us take the definition of Nusselt number, the primitive definition, okay, it is r equal to r naught, okay, that means at the wall T by T m, okay, this is of the order 1, right. Okay. So, that would mean there is a d over here, okay, that would mean that dt by dr r equal to r naught is the same as T naught minus T min, right, for any x, right. Remember that T naught and Tm both can be functions of x only, right, because the wall temperature and the mean temperature both are functions of x, because mean temperature by definition you have removed the variation with respect to r, right. So, on the left hand side whatever it is, on the right hand side whatever it is, okay, for any particular x this relationship is valid, right. So, therefore, we can argue that the x variation of dt by dr at r equal to r naught, right, is same as T naught minus T naught minus T mean, is not that so? Because otherwise for any x it won't be acceptable, right. So, for any x this relationship is valid, that means the variations on both sides must be the same function of x, right. So, that they kind of cancel each other out, right. Yeah. So, now we can have an important, so based on this, okay, based on this particular definition, okay, but T is normally, but when you define dt by dr say for example, right. So, dt by dr is basically nothing but the variation of the radial temperature profile. Now, when you look at dt by dr, what do you think that dt by dr's function is going to be, right. So, dt by dr is a quantity, okay. Dt by dr at r equal to r naught, that means you are specifying it at a particular thing that has an x variation, right, but that x variation is basically taken care of by whatever is the T naught minus T mean variation is, right. Okay. So, if I kind of conjure this up, that dt by dr by T naught minus T mean, right, what will be the definition, what will be the variation of this quantity, okay, because this quantity therefore, okay, the upper quantity is a function of both x and r, the lower quantity is a function of x only, okay. We know that when you evaluate it at any particular location for any r, okay, it kind of shows the same kind of variation, right. So, is there a possibility of writing this particular equation, using this particular equation, right, and stating that this is going to be a function of r only, okay, that is what our main objective is. So, we will stop here, okay. In the next class what we will see is that we will find out that how we can conjure up, okay, a definition for the temperature field, okay, a definition for the temperature field which is a function of r only, okay. So, see you next class.